Welcome to Regular Expression. This is Dr. Thieu Kim Hing, Informatics Academy. First, we discuss operation on formal language. Since language are set of string, we can apply standard set operation on languages, such as union, intersection, different, and complement operation. The unique operation for formal languages is the concatenation operation. The concatenation of two languages L1, L2 is defined as the component-wise concatenation from the string in the languages. Based on the definition of concatenation, we can define the power operation, where L raised to power n is defined as L concat itself n time. In particular, when n equal to 0, L to the power 0 is not empty set, but a set consists of the empty string lambda. In other words, L to the power 0 is the language consists of only one empty string. A note that L in this way, L to the power 0 concat L, which is empty string concat with L, will be back to L. Note that a language containing only the empty string is different from the empty set. For empty sets, it concat with any language will back to empty set. Based on the power operation, we can define the clean star operation. For a language L, the clean star denoted at L star is defined as the union of all the power of L. In other words, it is the union of L to the power 0, L to the power 1, and so on and so forth. In particular, if L is AB, so AB star will consist of all the string over AB, including the empty string lambda. Note that this is different from AB star because AB it contains only one string AB, and AB star stands for AB repeat itself any number of times, such as repeat itself 0 times, we got empty string. Repeat itself 1 time, we got AB. Repeat itself 2 times, we got AB, AB, and so on and so forth. Here are some examples of language operation. In this example, 0 and 1 concat together is a set containing only the string 0, 1. 0 star contains the string of 0 only, any number of 0. And these two concat together, we will have 0, 1 followed by any number of 0. 0, 1 followed by empty string, 0, 1 followed by 1, 0, 0, 1 followed by 2, 0, 0, 1 followed by 3, 0, and so on and so forth. The next one means any string over 0, 1 followed by 0. So in other words, this represents the language that ends with 0. For example, this will end with 0, end with 0, end with 0, and so on and so forth. This is the intersection of two languages. The first language ends with 0. The second language is 0, 1 square, which contains string of length 2. So the intersection means the string of length 2 and end with 0, which is 0010. This string with links 2 and end with 0. That sigma be a finite alphabet and A be any character within the alphabet. A regular expression over sigma can be defined recursively as follows. First, the basic case. We got this symbol represent the empty set. Lambda represent the set with empty string. A represent the set with A itself as the only string. From the basic, we can form complex regular expression using the union operator, concatenation operator, and green star operator. The union operator is denoted as the addition operator. So E1 plus E2 means the two language union together. E1 concat E2 means the two language concat together. E star means the language itself apply green star operation. For example, this one represents any number of 0 followed by 1 followed by any number of 0. That means the language containing of string with only one 1. This regular expression represents any number of 0, 1 followed by 1 followed by any number of 0 and 1. In other words, it's the string that contains at least one 1. You may have many 1 in front and many 1 follow it, but you must have at least one 1. This is a regular expression for a language that contains 001 as substring. In front of 001 can be any number of 01. And after 001, we can have any number of 01. This is language 0 plus 1 concat together. This actually is the string with links to 0001 1011. And this string of link to apply green star operation, we got a language containing all string of even link. Link 0, link 2, link 4, and so on and so forth. Given two finite automata M1 and M2 that accept language L1 and L2 respectively, we assume that M1 is a non-deterministic machine with initial state x1 and one final state y1. Similarly, for M2, its initial state is x2 and it has only one final state y2. We would like to construct machine based on M1 and M2 that will be able to accept composite language such as L1 concat L2, L1 union L2, L1 green star, L1 intersect L2, L1 complement, and L1 subtract L2. We are going to do it with a simple case study. Consider these two machines M1 and M2 that accept language L1 and L2 respectively. M1 start from A and it will alternate the state from A to B when it receives symbol 0. It's quite obvious that A actually recognize the string with even number of 0, and B recognize the string with odd number of 0. Since A is a final state, so L1 is the set of string that contain even number of 0. For machine 2, when it see a 1, it go to a final state. In other words, it will recognize all the string that end with 1. Based on these two machines, we would like to construct finite automata that recognize L1 concat L2, L1 unit L2, and so forth. Let's start by looking at the concatenation operation. Recall that concatenation means we have a final set of string that can be divided into two parts, where X belongs to L1 and Y belongs to L2. In other words, X can be recognized by first machine and Y can be recognized by the second machine. So what we can do is construct a machine that starts from A, the initial state of the first machine, and that they run when the first machine go into the final state A also. We apply a lambda move to the initial state of the second machine. Then we let the second machine run. When the second machine go into the final state Y, then we got a string that consists of the first part recognized by first machine and the second part recognized by second machine. In other words, we have a machine that accepts concatenation of L1 and L2. Now we look at the union operation. We can construct a new initial state, and that the new initial state perform a lambda move to the initial state of first machine and the initial state of the second machine. Because of this non-deterministic behavior, the resulting machine will be able to accept any string accepted by first machine or the second machine. In other words, we will have a machine that can accept the union of L1 and L2. Given L1, which is recognized by machine M1, we can easily construct a machine that recognizes L1 prime, which is the complement of L1, by changing the final state. For example, in the first machine, A is the final state and B is the non-final state. We swap it. So if the first machine go into final state, the second machine will go into non-final state and reject it. If the first machine go into non-final state and reject the string, the new machine will go into a final state and accept the string. In this way, the new machine will recognize the complements of the language recognized by the first machine. Next, we look into the clean star operation. So, given the language L1 recognized by these machines, clean star means what? You will be able to allow the machine go into loop from its initial state to final state many times, including 0 time. So what we will construct is a new initial state. From the new initial state, we perform a lambda move to the initial state of the original machine, and that the machine run until it go into the final state, in this case also A. From the final state, we make a lambda move back to the Q0. So if needed, from Q0 we can make a lambda move to A and perform operation of the original machine until it go to final state A and back to Q0 again. And we can do it any number of time, include 0 time, because Q0 is also the final state of the new machine. In this way, we develop a new machine that can accept the green star of L1. Finite automata are limited. It can only recognize regular language. A lot of important language are not regular language. For example, the language consists of the same number of A followed by same number of B. This is not a regular language. The proof is like this. Assuming that we got the finite automata that accept this language, and this automata must have finite number of states, let's say K. Then we purposely fit this machine with a string with huge number of A, for example AR, BR, where R larger than K. Then that this machine executed. And this machine, because there are more A than in the state, so this machine must visit some state twice, and therefore form a cycle of R level A. This cycle of R level A can be looped many times, and therefore it's not just accept AR, BR, but A R plus P, BR, where P is the number of A in the cycle. But this AR plus P, BR should not be in the language, because language should have the same number of A and B. In this way, we establish a contradiction. Therefore, there should not be a automata that accept L, and therefore L is not a regular languages. Let's summarize what we learned from this chapter. A regular expression provides an algebraic approach for concise description of string in the regular language. We will see that we can have grammatical description using so-called regular grammar for regular language too. Of course, we have seen procedural description or operation description of regular language using finite state automata. It can be proven that these three mechanisms, finite state automata, regular expression, regular grammar, are equivalent, meaning that the type of language that can recognize or generate are the same, and they are all called regular languages. We have proven that regular languages are closed under concatenation, union, green star operations, intersection, complement, and different operation. We have also seen that there are limits on finite automata. there are languages which are not regular language. A powerful tool to prove non-regularity of a language is the pumping lemma for regular languages. This is the end. Thank you for your participation.